All right, welcome back to Lecture 1B, CSE 215. So we're talking about sets. One thing we're definitely going to want to understand about sets is equality. What does it mean when we say two sets are equal? So let's say we have a set A and a set B, and we claim that they are equal. What this means is for all elements X that might belong to a set, X is contained in A if and only if X is contained in B. So if X is contained in A, it's contained in B, and if X is contained in B, it's contained in A. In other words, sets are collections of objects, right? An object belongs to this set precisely when it belongs to this set, and vice versa. So the collection of things is the same. Again, order doesn't matter. Right, here's one set, 1, 2, 3. Here's another set, 3, 1, 2. Are they exactly the same set? Absolutely. Why? Because any number that belongs to this set belongs to this one, and any number that belongs to this second set belongs to this first set. That's all that you need to say that these two sets are equal. And so you can see why order doesn't matter. So for all X, we have a symbol for this, which we'll talk more about later, but we'll abbreviate it sometimes with this upside down A. This means for all X. And if and only if we'll abbreviate with IFF, just because we're going to use these things very often. So we could say for all X, X is contained in A, if and only if X is contained in B. And that's shorter to write, and it looks kind of cool, so we'll stick with things like this. All right, so you're probably familiar with Venn diagrams. So Venn diagrams are a way that are going to be useful to help us analyze things about sets. So we typically draw a box for the entire universe, and I'll call the universe U. So U equals the universal set. And this might be the set of all foods. And when I have some other set, I'm just going to draw a circle, and I'm going to label it. So this is a set C, and C equals the set of cookies. And here's another set H, and H is the set of foods with chocolate. So H is part of the universe, right? Anything that is a food with chocolate is also a food. And C is part of the universe. Anything that is a cookie is a food, at least in my universe. And we can talk about elements of this set. For example, inside this set is an element called a snickerdoodle. If you haven't had snickerdoodles, you're missing out. It's a really good cookie, cinnamon and cream of tartar. Over here in the set of foods with chocolate is something called M&Ms. And over here, there might be something that belongs to both sets. What would this be? This could be a chocolate chip cookie. It's an element of the set C because it's a cookie. It's an element of the set H because it's a food with chocolate. And it's an element of the entire set U because it's a food. So we can see some things by looking at this diagram. We can see, for example, that these two sets overlap, whereas over here might be a set V, and V might be the set of vegetables. And I'm sure there's some universe where there are vegetables that are made with chocolate, but in this universe, vegetables are neither cookies nor things made with chocolate. It's disjoint. It has nothing in common with the set C or the set H. Whereas C and H have some things in common. There's chocolate chip cookies and there's other things that overlap in these sets. So a Venn diagram, right, this is a Venn diagram, two ends, can help us sort of picture relationships among sets and look at things like overlaps or when sets don't overlap one another and so on. We're going to use fairly rigorous techniques to analyze sets, but this can be a visual way to help us sort of gain some intuition about what's going on with a set. All right, so hold Venn diagrams in mind, and let's talk about other properties of sets. So a key property is a subset. So what do subsets mean? A is a subset of B if and only if for all elements in A, X is also an element in B. So to say A is a subset of B, we write the symbol A and then this sort of sideways U with a line underneath it. Okay, this means is a subset of. So A is a subset of A if and only if for all X in A, X is contained in B. Similarly, we can say A is not a subset of B if there is some element X in A such that X is not in B. In other words, if there's some element in here that's not in B, then A is not a subset of B. So for example, let the set S equal 2, 4, 6. Let the set T equal 2, 4, 8. And let the set V equal 2, 4, 10, 6, and 5. So S is a subset of V because every element in S is also in V. 2 is in V, 4 is in V, 6 is in V. But S is not a subset of T because there's an element 6 in S that doesn't belong to T. So think about Venn diagrams. If you draw Venn diagrams of sets, what does it look like when something is a subset or something is not a subset? So we'll experiment with that on the board. So here's our first theorem for any set S. S is a subset of itself. And why is that true? To say that this is a subset of that means that any element in here also belongs in here. Well, any element in S is clearly an element of S, right? That's sort of obvious, right? But that's enough to say, therefore, S is a subset of A, because S is a subset of S means if X is an S, then X is an S. And that's always true. So S is a subset of S. Here's a little bit weirder one. The empty set is always a subset of any set S. And why is that true? Well, now we start to get into something that's going to be a little weird when we talk about logic, which is this idea that for this to be true, we need to know that any element in the empty set is also an element of S. Well, there are no elements in the empty set. So this does not fail to be true, okay? And this can feel a little weird because since there's no elements in the empty set, how can we say that any element here is also an element of S? But when we look at truth values, we're going to basically say there's nothing that makes this statement wrong, right? This says that for any element in A, it must be in B. Well, for any element in here, it must be in S. Is there an element in here that's not in S? No, because there's no elements in the empty set. So every element in here belongs to here, and so this is a true statement. And certainly because of both of these, the empty set is actually a subset of itself. Okay, so that's going to be a hint of where some of the weirdness can come in when we start dealing with sets in an abstract notion. So one more comment on subsets. We just finished saying that for any set S, S is a subset of itself. But that's not interesting to us, right? We know that any set is a subset of itself. So we're going to have a slightly different notion, which is called a proper subset. So A is a proper subset of B, and we're going to write this with this slightly modified symbol with a little slash through the bar here. And this means A is a subset of B, and also A is not equal to B. So a proper subset means a subset that's somehow more interesting than the set itself, right? So to say A is a proper subset of B means that it's a subset, but it's not equal to B. So it's somehow more interesting than just the case where, you know, B is a subset of B or A is a subset of A. All right, well, something we can do with subsets is another theorem. So here's a theorem. A is equal to B if and only if A is a subset of B and B is a subset of A. And I'm using a symbol here for and. We're going to see some more symbols for ands and ors, but this just means and. So two sets are equal if and only if each is a subset of the other. A is a subset of B and B is a subset of A. And if you go back to your definition of what it means for A to be equal to B, it means every element in A belongs to B and every element in B belongs to A. Well, since every element in A belongs to B, that means A is a subset of B. And since every element in B belongs to A, that means B is a subset of A. These are just the definitions. So this isn't even quite a theorem. This might be more just a note or an observation. But this is a powerful way, if we want to know if two sets are equal, we can show that two sets are equal by showing two other things. Show that A is a subset of B and show that B is a subset of A. And sometimes these things are easier to show than directly showing equality. So that's going to be something that will be useful for us down the road. All right, so next set of lectures we're going to start looking at more operations and some properties of sets.